Anatoly Libgober that will talk about Motivic infinite cyclic curves.
Thank you, organizer, for wonderful hospitality. It's very happy to have the opportunity to speak here. Well, I followed Pepe's work from the very beginning, so from his thesis to studied the frame manifold, in particular. Can you have the phone? Aha. Is that better?
Yeah.
Okay. Right, and so that time, so he studied Z2 invariance which comes by looking at R invariance on quadratic form. And I also happen to study Kerber invariance, another invariance which comes from R invariance of quadratic form. And then after that, so we were corresponding, and I think we met in Mexico in Lefschetz Symposium in 1984. And since then, just for following great work on singularities. And well, some of that singularity, Milnor fibers of metamorphic functions actually will come up a little bit later in this talk. Okay, so the title, so what I'm talking today, it's Motivic infinite cyclic covers. So that's a joint work with Manuel Gonzalez Villa and Lorenzo Maxi. So if you happen to get interested, so that's, you can look at the archive in this whole paper. Let me say a couple of words for where I'm heading. So, what I will be looking at regular neighborhoods of divisors with normal crossing. So we'll look at the algebraic variety, projective, quasi-projective, and the union smooth subvariety intersecting each other is normal crossing. And we'll look at the regular neighborhood. So that's what this T star is. And so basically we want to understand algebraic geometric invariants which are associated with this. With this tubular neighborhood. Well, perhaps if you first looked at such equations, Alan Duffy in the 80s, who constructed the mixed-watch structure on this neighborhood. But I want to talk today about something else. Instead, so what I do, I want to throw out from this neighborhood the divisor itself, that will be a punctured neighborhood. And then I want to take infinite cyclic cover. And to that, so I associate some Euler characteristic. But Euler characteristic, not integer value, but some K group of motives. And introducing this absolute object has an advantage. It's at the same time you assign many other invariants. And how you come down from this more complicated invariance to simple invariance, so I'll explain a little later in this talk. So why are we interested? So why are we interested in that? Well, it turns out that this construction, so this construction where you look at invariance of infinite cyclic cover actually leads to invariance in many parts of singularity theory. So in particular, if you have Milnor fiber, so the invariants of the Milnor fiber, such like monodromy or spectrum, so they all we can detect it using this construction. Or recently, so the people look at the Milnor fiber associated with polynomials near infinity, or the Jones of metamorphic Milnor fiber associated with Jones of metamorphic functions. So those invariants of these Milnor fibers also one can get a special case of this more general scheme. Well, so that's sort of the goal. So generalize, basically the goal is generalize the various incarnation of Milnor fibers which comes up in singularity theory. Okay, so I'll start talk about one of these topics. I'll talk about infinite cyclic cover, then about finiteness conditions, that's, which allows to assign this early characteristics in a meaningful way. Then I'll talk about virtual motives, about this big K group, and then discuss this invariant we should define, and finally I'll talk how this invariant related to the Milnor file. Okay, so that's the plan. So now let's just see a little details what we're looking at. So I'm looking at infinite cyclic cover. So what are covering spaces? Let me just remind some of the basics, which often come up undergraduate courses, but it's good to review this. So the covering space, it's a map of now, covering space is a map P from topological space X over X, which is locally trivial fibration in discrete fiber. So now there is a description of the covering space actually in terms of group theory, and that goes as follows. So first you fix a point on a base of the covering, and then you fix a point X tilde above it, so which map P takes into, and then you look at the induced map of fundamental groups. So that gives you subgroup in fundamental group of X, and simple theorem says that there is one-to-one correspondence between subgroups of the fundamental group and the covering space. So between subgroups and covering space. Now there is this important thing to remember about covering space. There is action of fundamental group on the fiber of point X. So just because it is discovered in the atomic property, so if you have closed loop here, you can lift it. Yes, you cannot hear me. Okay, you cannot hear me. Okay, let's try that. Okay, let's see what you get. Okay, so okay, there's some echo. So we have this fundamental group of X acts as a automorphism group. Automorphism group of fiber is by lifting loops which don't lift in general into closed paths. But now the special class of coverings, so it's coverings for which fundamental image of fundamental group of subgroup of fundamental group which defines covering is actually normal. So we call such coverings the raw coverings. So that's geometrically that means that all lifts of the loop downstairs actually are closed, all are loops. Okay? And so in the case of normal coverings, so that's this covering subgroup is normal. So covering actually specifies by factor group, by quotient group, and homomorphism of fundamental group and quotient. Okay, so we'll be interested in particular with the covering this cyclic algorithm. So we have space in some fundamental group which have subgroup quotient by which is cyclic. Okay, so here's some typical examples. Also exponential map, which have C numbers, C star, complex numbers non-equal to 0. So that's an infinite cyclic cover. So fundamental group here is C, and so that's cover corresponding to subgroup. That's to trivial subgroup. So if you can look a little bit more general, so that if you take a C star to the R, complex terms. So then actually cyclic cover also is homotopy equivalent to retract of the torus of dimension r minus 1. So it's a good exercise, and that will come out. So here it's the torus of dimension 1, so that you get homotopy equivalent torus dimension 2. Okay, so, and now let's look at the next example, very close to the first one, in which, so we take now infinite cyclic cover another C star, but throw out the point, another point, like 1. So we take the image of 0 and we take the image of 0 and 1 and remove. So pre-image of 1, so if exponentiation we take an exponent 2 by iz, so that the image of the 1 will be all integers. So if we restrict this cover on the complement to 0 and 1, so then you get cover as a cover C minus all integer cover. Now you can ask what the homology of this cover? Well, H0 will be 0, but H1 will actually infinitely generate. And so this is an infinite. So here we have an example of the cover where homology of the infinite cover have infinite dimension. Now notice, in this correspondence between surjection onto Z and infinite cyclic cover, so this cover corresponds to the map which sends loop around 0 into 1 into generator Z, and loop which goes 0 around 1 actually goes to 0. That's the homomorphism which you find this. Which you find this. Okay. Now, what is connection with the Milnor fibers? Well, it turns out Milnor fibers can be interpreted as infinite cyclic clouds. Okay, let me tell how it's happened. Well, Milnor fibers will put. Milnor fiber. So we take a singularity of F, and then we perturb it and perturb hypersurface F equals 0. So we intersect with small code. So we get a complex manifold with bound. In fact, we get Stein manifold. So now that Milnor fibration theorem tells us that we can fiber complement involved to F equals 0 over the disk. And then what we can do, we can take infinite cyclic cover of the disk, well, it's the same exponential map which we just saw in the previous slide, and then we can take fiber product. Fiber product. So this is the now for the fiber of the map F. Just clearly I can identify with the fiber. It's homomorphic. You can identify with the fiber of this map. And on the other hand, so we have this. We have local interior vibration over T, so this whole vibration is homotopy equivalent to the Milnor fiber. So on one side we have infinite cyclic cover. We have infinite cyclic cover of the complement. Right? We have infinite cyclic cover of the complement. On the other hand, this infinite cyclic cover is homotopy equivalent to the Okay, so now Milnor finite CW complex. That's another thing which Milner proved at the time. So that means that all the homology group are finite dimensional, and moreover they are all vanishing dimensions sufficiently long. Okay, so but we already saw, so from the point of view of infinite covers, that's a non-trivial fact. That at least in the case of Milner fiber, we have covering space which has this finite problem. Yes?
Closer to me.
Oh, okay. Thank you. Right. Okay. So, and this sort of finite dimensionality of infinite covers is a very similar situation. Actually can disappear. So another interesting case, so there are actually abelian analogs of the Milner fiber. So Milner fiber was cyclic cover. Because if you have irreducible germ, so then homology of the complement is just H1. So and the only abelian cover which you have is cyclic cover. But if you take reducible germ, like which has R components, then situation is different. So it's, if you have reducible terms, so there are non-cyclic, abelian non-cyclic covers. That's one can see as follows. So, well, so homology group, here it's just free abelian group with R generated. So we clearly have abelian covers. And if you take maximal abelian covers, so then unless this product of this F1, Fr is devised with normal crossing, unless you have normal crossing, so you will have all this infinite generated homology. In fact, so if a dimension of this ball is n, so suppose dimension is 2. Dimension is 2. So then what you can show that H1 is actually again identified with the ring of Laurent polynomial quotient by just Alexander polynomial in 2 variables. If in R variables, if your divisor has R component. Right. So in this case, if the dimension of this ball, for example, is 2, so then if first homology group of infinite abelian cover here, it will be just ring of Laurent polynomials in R variables quotient by principal ideal generated by Alexander polynomial in R variables. And if you take a ring of polynomials, ring of polynomials really in 2 variables and quotient by principal ideal, you get infinitely generated vector space. So if you take abelian analog of this Milner fiber, so you automatically will have so that's sort of just trying to convince you that the issue when infinite cover has finite dimensional homology, it's interesting. So it's good to isolate these situations. Okay. So now let's look at the. Any questions? All right. Now let's go to this specific setup which I already mentioned. Now it goes as follows. So we start with quasi-projective variety, smooth quasi-projective variety, which can be compactified to smooth projective variety X bar. Yeah. So I'll be looking at a normal crossing divisor. So it's a union of irreducible components which all are smooth. So it's important that once you have this the normal crossing divisor, you have stratification. Of the union. So and this is strata labeled by a subset of the set of indices. So that set of indices I. I'm sorry, J, set of indices J. So it's, and so the strata with a labeled subset is just intersection of components. Okay. So, and so now that it's important open subsets, which one you consider is EI0. EI0. And the main point which we'll use, so that is well, it's not my stuff. Why doesn't work? Okay, so now, now important point here is that this punch neighborhood. Okay, let me remind you. So what is that? So I take this x and I delete. If I take x, delete e. That's what's punch neighborhood. So that's union of this complex star of various dimensions. Dimension of which determined by this set of indices. So here's an example in the case of surface. So let's see, it's two-dimensional case. So we have this red arcs, these are these divisors, and so that and this there are only either single divisor or double intersections. So the I can have either one or two elements. And so EI, what EI0 corresponding to this component is just this whole component minus the intersection of other components. And so the restriction on this tubular, punch tubular neighborhood, this component is just a C star. And if you take this point, so here you have this disk, and you remove two lines, then we have that system. So it's previous thing, right?
Anatoly,
Yes.
do you think it's a bound in the classical topology or in the Savinsky topology?
I'm sorry?
In which topology you speak of bound? Algebraically in Savinsky topology or in classical topology?
No, that's classical.
It's topology.
Yes, yeah, absolutely. Okay, now now it's important to spell out the equivalence relation between this neighborhood, because in some sense it tells us what kind of object we're working with. So of course we can view this T star X as a complex manifold. Well, but we know that to define Hodge structures, so we need a space with algebraic structure. So this complex structure won't be enough. So this definition of equivalence rigidifies the kind of objects that you consider. So so equivalence relation is the following. So this two-punch neighborhood are equivalent. So this two-punch neighborhood of two divisors in different varieties. X1 and X2 divided by 1 and 2. If there exists a birational map, and by rational map, I mean a map which is defined not everywhere, Zariski open set. Map defines Zariski open set and its inverse defines Zariski open set. But to have the equivalence of this neighborhood, so we have to have birational map such that phi is regular on punch neighborhood. And inverse will be also on punch neighborhood, and so it takes this punch neighborhood somewhere in X2 bar. And so we want that this X2 bar will land inside. And so there will be one will be deformation with track or another. So that tells you what does it mean that to name it. Well, and of course, I also want to look not at just punch neighborhoods, but equivalence of the infinite covers. So that condition of equivalence in infinite cover, that's commutativity of this diagram. So that's where we'll use so here we use delta subjection delta 1 to construct infinite cover. So if map phi identifies delta 1 and delta 2, so then let's say then the infinite covers. Okay, now we come to definition of the cover of the finite type. Because we want the cover of cover of the finite type of the punch neighborhood is the cover for which the following condition is satisfied. Now, with each delta, with each divisor EI, so we can associate a loop boundary of the transversal disk, is delta I. So we want that the image under the subjection which defines infinite cyclic cover will be non-zero. And we also can in fact, we also can change delta I to make it positive. So essentially, this condition necessarily follows from this example, which was one first example, the infinite cover, which has infinite time. So, but what one can prove that, in fact, that if this condition is satisfied, it's delta delta I. So then the cover is in a finite time, in the sense that the cohomology are finite dimensional and vanishing above sufficiently large I. Sufficiently large. Okay. Now let me tell you, there is some technical step which go in the proof of this. So I want to spend a couple minutes to explain it. Well, so the technical step is sort of just to understand coverings of the fiber spaces. So now we'll look at the locally trivial fibration A over B with fiber C. So there's local fibration, and so the claim is that if we have a covering of A with group G, right, and that's suppose we have covering of A with group G, so that's given by the subjection from the null group of A of total space of this locally trivial fibration onto G. So firstly, such covering gives us a covering of the fiber. It gives us a covering fiber C, because just below our group will be just so pi one of C, so quotient of pi one of C is subgroup of pi one of A. I didn't write zero there. So the quotient of pi one of C is subgroup, so the quotient has subjection over H, so therefore pi one of C itself has subjection over H. And so the claim is that in fact, so that allows us to give to find the cover of the C of the fiber, and then this cover of the total space fibers of the cover of the base, with the fiber which is the cover of the fiber, this fibration. So, but what's also important here, so that what's important here, so the Galois group of this covering of the base is G mod H. G mod H. So notice in particular, if G happens to be Z, so if you're looking at infinite cyclic cover of the total space, and if subgroup H, is non-trivial, then the quotient must be finite. So in other words, B tilde B tilde is actually finite cover, and so if B is finite dimensional, then B tilde also will be finite CW complex. B tilde also will be finite CW complex. You will have finiteness of homology. Okay, so that's this technical step which identifies which tells what's happening with locally real vibration equal to infinite numbers. And so that's essentially repeats what I just said. So basically, we already saw that the T star of E, Punch neighborhood, is union of toric vibration of this quasi-projective variety, EI0. EI0. So that's so we have this vibration. So and once we have infinite cyclic cover, so just by previous slide, so we have infinite cyclic cover, fiber over finite cover of EI0 with the fiber which is infinite cover of the torus. But torus has this remarkable problem that all infinite covers of the torus actually have finite dimensional homology. So that's why this finite type condition is satisfied on over each stratum. So then my recursive shows you finite dimensionality of this whole homology of infinity. Are there any questions? Okay. All right. So now we know sort of what is the condition under which sort of the homology of infinite finite dimension. So well, in particular, if you want to have mixed plot structure, let's say, for on homology of the infinite cyclic cover. So that's a clear minimal prerequisite for having mixed plot structure. The spaces in which you put it, they must be finite dimensional. So at least we know condition when we can expect. Okay. Well, so in fact, so what we'll put, we won't put the mixed plot structure in homology. If we do something, well, in some sense weaker, but in some sense more general. Okay, so now we'll see how that goes. So now the invariant which I want to associate with infinite cyclic cover, this function is in fact it belongs to a K group of varieties of C. What is that? You just look at the free abelian group generated by all quasi-projective varieties, so it's not condition. And then you consider subgroup generated by this relation, for any subvariety Y, so you want that that's the condition will be satisfied. So the ordinary topological order characteristic is additive. So in particular, so if you portion by this relation, so you definitely get from one K0 variety into C, which is given by order characteristic. So in this sense, K0 variety is the receiving object of for this universal order characteristic. Well, in fact, so we'll need to look at the version of this K group. We'll want to look at the varieties which are action of the finite cyclic group, okay, and subject to certain relations, which I didn't write down, but essentially the same scale. Okay, and now what I just said, okay, so there is an important point here. This is a abelian group, of course, because we started with 3 abelian group generated by this classical projection, right? But it's also a ring, which is product of varieties, induces multiplicative structure. This multiplication, that becomes ring. This is very interesting ring about which known actually quite little. Well, the standard part question about zero divisors. Well, so it's known that zero divisors, but for example, even if a class of a fine line is zero divisors. So interestingly, it's very large. Well, but what's nice about this ring, it has a lot of morphism and much simpler rings. So in these rings, so there's something called realization. So here is an example of this realization. So about one example, because I just said this other characteristic. Take variety and take characteristic, and then the receiver of this. So then R will be Z, just ring of integers. And this other characteristic, so you get some gives you this realization of elements of the K group. Well, there's another better realization, so where you take into account the action of the finite group. Once you have variety with the action of the finite group, incidentally, so mu hat actually stands not for finite group; it stands for profinite completion of Z. So, but this having continuous action of this profinite group is the same thing. Some finite group of finite cyclic of some. So that this notation allows me not to specify order of the group. Right. So if you have now, if you have the vectors, so I want to construct something which is called Pepe realization. So in constructed, actually, I'm looking at the category of vector space together with the morphism. Okay, I look at another category. That's what mentioned. Category of vector space together with the endomorphism. Now it's not hard to show that this K group, so you can run the same construction. Look for the free abelian group generated by these pairs, and then quotient by a subgroup. Well, subgroup given by a relation given by exact sequences. So then you get this K theory of group of vectors, of category of vector spaces within the morphism, which you can, as you know from linear algebra, so it's the same as category of torsion modules of a ring of polynomials. So and this K theory here you can identify that this quotient, ring of rational functions, quotient by Q, and the homomorphism is given by just associating to vector space. Well, I'm a little bit mixed up. So this Pepe realization associated to vector space and the morphism, just characteristic polynomial, or maybe one more characteristic polynomial of this morphism. And now, if you have topological space that has cohomology, various dimension, then you look at the zeta function of the morphism. So here actually, I see. So V here is not vector space, but actually some variety together with the morphism. And this variety has homology, various dimensions. So on which the morphism T acts, in fact, topology, and then you look at the zeta function. So, and the big serialization just associates to this variety here is a zeta function. So there are other realizations of co-realization, so which uses the fact that quasi-projective variety is here generated. They have mixed such structures, so you can associate this K-theory of Hodge structures, and we have this realization. This group still complicated, quite interesting. So, but it has another morphisms with a much simpler group, which we'll talk about later. Okay, now we come to the main definition. Finally, suppose we have a quasi-projective variety. E is normal constant divisor, and so we have delta. Well, which I didn't write here, but it's something. Homomorphism delta fundamental group of punch neighborhood of E into Z, which defines infinite cyclic power. Right, so in other words, so that's the infinite cyclic power, which for motive for which I want to define. So now. Over each stratum, so we have over each stratum we have this C star to the R fibration. We have torus fibration, which we discussed before, and so this the torus fibration is actually subset here. So that if we restrict this infinite cover on the stratum EI0, so we restrict. We get the infinite cyclic cover of torus vibration over this star. So, and from this technical discussion which I had before, so it gives us finite cover. It gives us finite cover. So it's important. Just that's the main point. Once I have this infinite cover over each stratum, I automatically get finite cover. To get a finite cyclic cover. Okay, and that's what this E0I is. So, and then I'm just form this element in this group, the group of variety. Okay, so well, okay, so that's definition. So now, what it's good for? In fact, even doesn't make sense. That doesn't make sense. Well, so what we want it will be invariant of this complex manifold with some algebraic structure. So we want to have this. So what will be too narrow? If that will be invariant of X pairing X and E. What I'm saying is, in fact, that invariant, which we define, it's invariant not just pair of X and E. It's invariant of pairs X and E under this equivalence relation, which we saw earlier. So that's what this theorem says. This Motivic infinite covers, so that would S is that's Motivic cover. So it's invariant equivalence between these pairs together. So now how the proof is going? Well, now what was my equivalence relation? So we said that two pairs are equivalent, two tubular neighborhoods are equivalent if there is birational identification of these two pairs, and when such that this delta homomorphism is defined in infinite cover, if you restrict the tubular neighborhood, they will be essentially compatible. Well, now the key step is magic weak factorization theorem, which tells that any birational map is actually can be obtained by a sequence of blow ups and blow downs. So therefore, well, in this diagram, so each arrow is blow up with the center with center blow up just on this divisor which we consider regular. So the main step is invariance blow up, and so it turns out that this formula has some consistency built in it, so that it's actually if you blow up, so which change your divisor, E and ambient varieties, that actually doesn't change this class in the K. Okay, so time is getting quite short. So I'll go just quite quickly. So we already talked about the Pepe realization. One of the features of the formula which I was writing is that if you take Pepe realization of this infinite cyclic cover, you actually get zeta function of the depth transformation. Zeta function depth transformation. I think that's it should be on this side. Right. So if you have infinite cyclic cover, this is so group C, the law group acts on Y tilde. And so since cohomology are finite dimensional, so we can form zeta function. So and so the proposition here, the Pepe realization of this Motivic infinite power is just zeta function. It is zeta function of the infinite power. Now there is also conjugarization, and so which we did talk about conjugarization depends on consideration of escape group of Hodge structures with automorphism, but it has actually homomorphism in a free abelian group generated by powers, rational powers of T. So, in Steenbring theory of Milnor fibers, so the Steenbring associate to Hodge structure with spectrums. Thanks. So there is Steenbring associate spectrum. So this conjugarization, which of the Motivic infinite cyclic power gives us spectrum of infinite cyclic power. And that's actually quite interesting since we don't even have mixed Hodge structure itself. In fact, that's what one of the problems here. Yeah. So the problem is mentioned is there is a spectrum of infinite cyclic power, but it does exist canonical mixed Hodge structure. Right. Now the last thing is the couple what I tell about relation to Motivic Milnor fiber. So if you have a germ of hypersurface in finite dimensional vector space, so essentially you can take resolution of singularity. You take tubular neighborhood, take infinite cyclic cover, and the Motivic infinite cyclic cover will be the Neflo-Z. So maybe I won't even go further. I'll just tell so there are other versions of Milnor fibers. Milnor fiber associated with the rational functions, and actually there are Milnor fiber at infinity. I know somebody is impossible to even talk about Milnor fibers at infinity. So this construction actually allows to give it gives Motivic version of the Milnor fiber at infinity, and also Motivic version of the Milnor fiber associated with rational functions.
Any question?
How did you get this D-brick spectrum of your construction?
We just take conjugalization, and there is natural homomorphism, which was in previous. Let's see. Yeah, on this slide. So there is this homomorphism. So if I take an image of Motivic intrinsically covered here, I get this polynomial with powers of t which are rational numbers. So these powers, that's the spectrum. Because what is element here? That's this polynomial. So alpha that's exponent, that's element of the spectrum, and then that's
Any other question?
So at some point you asked for the images of the meridians of the equation to be positive.
That's right.
I guess that, non-zero is needed, but
non-zero it's enough. Yes.
But if you have, for example, meromorphic functions, maybe you may have both
Yes.
sides.
Yeah.
So your construction uses split factorization theory. And
Yes.
if you look at Motivic vanishing cycles, you have two approaches. One is split factorization, the other one is Motivic integration. So I would propose as an interesting question if one could get this construction through Motivic integration. Have you ever think about it?
Well, yes, but first definition, the Neflos there was going to Motivic integration. Well, that doesn't seem works here.
No, it's not clear. It's just to ask it as a question.
Yeah, definitely would be interesting in our approach.
Okay, so any other question? If not, then let's thank the speaker. And one quick reminder.